Look at this terminal. This is physical memory consumption for a Go service I deployed. It climbs past 200 megabytes, hits 450, and at the 30-minute mark, Kubernetes executes a harsh reality check with an out-of-memory kill. This service is a standard bidirectional gRPC streaming pipeline. It handles a moderate load, 500 concurrent clients, sending about 5,000 messages per second, generating roughly 10 megabytes per second of inbound data. The implementation is generated code, built to precise specifications. It handles context propagation correctly, opens and closes channels securely, and serializes protobuf messages without a flaw. If you look at the application layer, the logic is sound. It passes strict linting, sweeps through test suites, and clears every code review standard you can throw at it. This chart shows the initial behavior. Memory climbs from 40 megabytes up to 90, and then levels off. For establishing 500 active connections, allocating buffers, and warming up the framework, this initial rise is exactly what you expect to see. But the stability is an illusion. If you keep the load running past the first few minutes, the line breaks its plateau. It climbs to 120 megabytes, then 160, and keeps rising at a steady 20 megabytes per minute. The immediate suspect is always a memory leak in the application. But the Go garbage collector is running on schedule. Logs confirm it is successfully sweeping and freeing objects. The next suspect is an abandoned channel or a hung routine. Yet checking the runtime confirms the active Go routine count holds completely steady at roughly 1,000. Every receive loop and send loop is accounted for. The application is perfectly executing its instructions. But flawless source code offers zero protection when sustained streaming loads exhaust the physical hardware underneath it. This split chart reveals the core problem. The Go application's internal view, heap in use, sits perfectly stable at 110 megabytes, but process RSS, the physical memory consumed, blows past 280 megabytes. That massive 170 megabyte gap is memory the operating system considers critical. Traditional profiling tools like pprof will not help you find this gap. They track live, active objects. They are entirely blind to the massive cumulative churn of gRPC transport buffers, allocating and freeing large byte slices thousands of times a second. When the garbage collector frees byte slices, memory remains inside the Go runtime's boundaries. Using madv.need, Go lazily advises the kernel pages can be reclaimed, but hoards them. Reusing warmed-up virtual memory pages is vastly faster than asking the kernel for new ones. The cost of that speed is severe. Because memory isn't forcefully returned, the operating system still counts those hoarded pages against strict container limits. You fix this by taking control of the runtime's boundaries. You set an environment variable called go_mem_limit to roughly 80% of your container's maximum capacity. This single variable overrides the lazy behavior. When total memory approaches your specified threshold, the runtime is forced to aggressively surrender those hoarded pages back to the kernel, keeping the physical footprint in check. The Go runtime creates this upward climb by prioritizing allocation speed at the direct expense of the operating system's constraints. gRPC uses HTTP2, multiplexing hundreds of independent streams inside a single TCP connection. To manage traffic, the framework must maintain dedicated receive and send buffers for every single stream, completely isolated from the rest. HTTP2 regulates this with a flow control window. This is essentially a strict budget. It tells the client exactly how much data it is allowed to transmit down the wire before the server must acknowledge receipt. In a steady state, the server processes messages at the exact speed the client sends them. Data moves smoothly, and transport buffers remain tiny. But networks rely on microbursts. If a pause hits the server, the client keeps firing data. Incoming packets stack up, pushing the transport buffer walls outward. gRPC allocates memory to handle bursts, but rarely shrinks it. The temporary spike becomes a permanent fixture. Multiply that behavior across 500 individual streams, each encountering their own microbursts and hitting their own independent high watermarks. The aggregate result is a massive, unyielding wall of memory consumption. The first defense is setting max concurrent streams. Enforcing a hard ceiling on how many streams can share a connection creates immediate back pressure, forcing clients to wait rather than silently hoarding server memory. Next, you override the generous defaults by configuring initial window size. Sizing the flow control window specifically to match your network's actual latency profile restricts how much in-flight data the client is allowed to stack up. Finally, setting an explicit max rev message size ensures that these tuned windows cannot be completely blown out by a single anomalous payload slipping through the pipeline. Without strict transport limits, ordinary transient network bursts will stretch your connection buffers into a permanent, immovable memory floor. There is a third consumer hiding in the architecture. In reality, streaming clients drop and reconnect constantly due to network blips and load balancer rotations. This chart isolates the problem. The application layer reports a stable 500 active connections, but total connections created climbs into the thousands. When clients drop, gRPC retains the heavy HTTP2 connection state beneath it. Buffers and metadata stay alive in the background. Every high watermark established by every disconnected client becomes abandoned memory. And because of the lazy allocation logic we covered earlier, the operating system takes an incredibly long time to reclaim it. The definitive countermeasure is configuring max connection age on the server. This setting enforces a strict lifespan. When the timer hits, the server issues a graceful go-away frame, safely terminating the connection without dropping active requests. This forced rotation acts as a hard reset for the transport layer. It destroys the accumulated high watermarks, strips away the abandoned buffers, and places a hard boundary on total accumulated state. You will only know this is happening if you install a gRPC stats handler. Without telemetry on your connection creation rates, you are completely blind to this churn until it takes your service offline. Leaving connection life cycles unmanaged guarantees that your service will eventually exhaust its memory through the sheer accumulation of ghost transport states. Apply these operational constraints, and the memory behavior stabilizes. On the left is the default configuration hitting the wall at 22 minutes. On the right, the tuned service peaks at 180 megabytes and stays there indefinitely. We achieved this stability without touching a single line of the event processing logic. The business code is identical. This illustrates the structural difference between these two communication models. In a standard request-response architecture, the system naturally resets its resource state the moment a call completes. Streaming architectures inherently accumulate state. Connections persist for hours. Buffers expand but rarely contract. Treating a stream like a request guarantees failure. Building Go streaming services requires a non-negotiable operational checklist. First, you must force the runtime to respect the operating system's boundaries using GO memlimit. Second, you must destroy accumulated connection states by enforcing a strict max connection age. And finally, recognize that memory growth is not always a leak. If you deploy these limits and your memory curve flattens out high but stable, you are simply looking at an efficient, warm cache doing its job. While AI and standard engineering practices write code optimized for functional correctness, true production reliability requires manually configuring the invisible transport layers for physical reality.